What's up, algebra bros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to be taking a look at characterizations of invertible matrices, and today's a very big day because we're going to talk about the invertible matrix theorem. So in the last section, we noticed that one of our matrices didn't have an inverse, right? We tried to augment with the 3x3 identity matrix, and we tried to row reduce, but it just couldn't be done. So today we're going to talk about properties of the invertible matrix because not all matrices are invertible. We want to have a discussion there, right? So let A be a square n by n matrix. So we're only talking about square invertible matrices. There is such a thing as a left inverse and a right inverse. These are sort of pseudo inverses, not quite the same idea, but you know, that's not what we're going to be talking about. We're talking about square matrices. When we talk about inverses, we talk about true inverses. The following statements are equivalent. What that means is that either all of the statements are true or all of the statements are false. So if I can show that one of these statements is true, I know that all of the rest of them on the list are true as well. If I can show that one of the statements is false, I know that all the rest of them are false. So we only really have to work with one statement at a time. But let's go through this laundry list of different statements we have for our invertible matrix theorem. This is the invertible matrix theorem. IMT. Yes, I am. First, A is an invertible matrix. Right away, starting off strong. Second, A is row equivalent to the n by n identity matrix. Then we have A has n pivot positions, and a lot of these they sort of infer the same thing, right? You'd say, well, if it's, row equivalent to the identity matrix, then it's going to have n pivot positions for an n by n matrix. Then we continue on to say the equation AX equals 0, and this is the 0 vector, has only the trivial solution. So that's a natural consequence of what we just said. The columns of A form a linearly independent set. The linear transformation x mapped to AX is a one-to-one transformation. The equation AX equals B has at least one solution for each B in vector space Rn. The columns of A span Rn. The linear transformation x to ax maps vector space Rn onto vector space Rn. And then we have two statements that are pretty similar, but it's showing that it works on the left, it works on the right. There is an n by n matrix C such that C times A is the identity. And there is an n by n matrix D such that A times D is the identity. So I have, multiplication on the left and the right to bring me to the identity. And that A transpose, the transpose of matrix A, is also invertible. So interesting to think that if A is an invertible matrix, its transpose is also invertible. Now, there's a lot of different statements here on this list. The truth is that we're actually not done. There's more of these that we're going to build onto this later on. So keep these in mind, but we're going to end up adding more to this invertible matrix theorem. There's more stuff to talk about. And we would say the following: let A and B be square matrices. If A times B is the identity, then A and B are both invertible, with B equals A inverse and A equals B's inverse. So sort of an interesting idea to sort of keep in mind there. Now what we're going to do is we're going to take a look at some examples. We're going to try to determine if the matrices that we have are in fact invertible. And we want to keep in mind that to answer that question, we would just want to show what we have on this list, that one of these things is true. Because if one of them is true, then all of them are true. And let me just start off by picking on the things that I think are going to be the easiest to identify. So I think statement B, which just has us row reducing to the identity if possible, is great. Statement C, the number of pivots we have, is really good. And then even statement E is a really good one as well. The columns, if we can judge the columns based on whether or not they give us a linearly independent set or not. That's not to say that the rest of these aren't usable. We might even talk about using some of the other ones. But these three, at least, are some of the fastest ones that we can work with and the easiest ones to work with if we want to consider row reduction. Now let's go ahead and take a look at this first example. So here I have this matrix A, And since it's just a 2 by 2 matrix, what I could actually do is to answer the question if it's invertible or not, is I could find the inverse, right? I could say, well, a 2 by 2 matrix isn't that difficult. If I just go ahead and find the inverse, then I'll know if it's successful or not. But if I want to try to use something on the list, what we could look at here is we could look at the columns of this matrix. So the columns of A are these two column vectors, 1, -5, and -3, 15. And we'll notice right away that these are linearly dependent. Because if I take this first vector, this first column, and I multiply it by -3, what's it going to give me? Well, -3 times 1 gives me -3. -3 times -5 gives me +15. It produces this second vector. So they're just multiples of one another. -3 times the first column produces the second column. So in this case, we would say, okay, so then the columns of A are linearly dependent. So what did we say in our invertible matrix theorem? We said, well, I need the columns to be linearly independent. That's not the case. So that means statement E is false. Statement E is false, which means that all of the things on this list, every single one of them, are false as well. Either they're all true or they're all false. So here they're all going to be false, which means that A is not invertible. So then A is not invertible. So it's not an invertible matrix. Let's take a look at the second example. Here, similarly, since I have a 2 by 2 matrix, like we said earlier, if I just want to try to find the inverse, I could just find the inverse. And then if I can find it successfully, you'll notice if you try to do that in this first example, there's going to be an issue. And we're going to talk about why that is later on. We're going to start talking about determinants in the next chapter. So hold on that, but we'll hold off on that. We'll be talking about it. But you'll notice that if you go ahead and try to find the inverse, it's not something you can actually do. So you'd fail at that level too. But here for the second example, right, if I'm looking at this matrix that I have and trying to find its inverse, I likely would be successful. But what I could do is I could do what we talked about for that last example. 2 by 2 matrix is very nice, right? I have a lot of options available. If I look at the columns of this matrix B, so here I'm using B for the name of the matrix, doesn't really matter. So the columns of B are, I have this vector 3, 4, and this other column vector 5, 6. And you'd say, well, are they going to be multiples of each other? Well, in fact, they're not. So we'd say if I tried to do that, let's say I didn't realize that by inspection. Let's say if I multiply this vector by 5/3, and you'll see why I picked that. It's going to give me that first entry, but it's going to fail otherwise. We'd say, well, if I multiply this through, 5/3 times 3, the 3's are going to cancel, it gives me 5. But then 5/3 times 4, this in fact doesn't reduce at all. 5 times 4 gives me 20 over 3. And 20 over 3 is not 6. So that's not going to produce that other vector. These vectors are not multiples of each other. So the columns are linearly independent. And it's because they are not multiples of each other. Moreover, like we've been saying, if you tried to find the inverse of this matrix using that closed form that we had a couple lectures ago, you would be able to do that successfully. You can find the inverse of this, and you'd be able to say, well, not only is it invertible, but here is its inverse. So lots of options for this, right? You could even treat it very directly. But since the columns are linearly independent, statement E here, linearly independent set, the columns of the matrix, in this case it's matrix B, form a linearly independent set. That means that matrix B is an invertible matrix. So that means B is an invertible matrix. All those statements on that list should be true. Let's take a look at this matrix C. We're just going through the alphabet here. And if I was looking at it, I think you might even be able to tell by inspection what the result is. But if we're trying to be on our best behavior, and really justify the work, we want to make sure that we're corroborating. And, especially on like a large assessment, we'd want to make sure that we're showing that we definitely know, not just by, oh, I looked at it and I can tell you about it. It's like you justify it, right? Justify it. But so let's go ahead and actually try one of the other statements. I'm a big fan of the row reduction. I want to know, will this matrix C be row equivalent to the identity matrix? So what I can do is I can actually row reduce it entirely. Let's row reduce it, right? So what I can do is I can actually start by scaling row 1. So let me do a 1/4 row 1. So here, dividing everything by 4, I'm going to get 1, 0, 0. And I can rewrite the rest of these. Don't really have to worry about doing anything fancy with them yet. But now what I can do is I can use this 1 in the upper left corner to get zeros underneath it. So that means I want 6 minus 6 times 1. So I'm going to replace row 2 with row 2 minus 6 row 1. And then I'm going to want negative 4 plus 4 times 1. So I'm going to replace row 3 with row 3 plus 4 times row 1. And that should do what I want it to do. So let's see, 6 minus 6 times 1 gives me that 0 that I wanted. 2 minus 6 times 0 gives me 2. 0 minus 6 times 0 gives me 0. In row 3's position, negative 4 plus 4 times 1 gives me 0. 3 plus 4 times 0 gives me 3. 7 plus 4 times 0 gives me 7. And from here, it's really short work, because what I can do now is I can reduce row 2. I can do 1/2 row 2. So I have row 1. If I divide everything in row 2 by 2, I get 0, 1, 0. And then I can just rewrite row 3, leave it as it is. You can see I'm only just a couple steps away from what we probably already were guessing about this. Because now I can use this 1 in the second entry of row 2 to get the 0's already above it, but to get the 0 beneath it, where this 3 is. So I can replace row 3 with row 3 minus 3 times row 2. So I can rewrite row 1, I can rewrite row 2, but in row 3's position, I get 0 minus 3 times 0 gives me 0. 3 minus 3 times 1 gives me that 0 that I wanted. And 7 minus 3 times 0 gives me 7. Now I just have to scale, right? So we'd say, well, let's do a 1/7 row 3, divide everything in row 3 by 7. So rewriting rows 1 and 2, and then dividing by 7 in row 3, I get 0, 0, 1. And this is the identity. So this has reduced to the 3 by 3 identity matrix. And now if you're thinking about, writing to me, well, why couldn't you have stopped at some point and said, well, look at where the pivots are going to be? That's fine too. I think this is a very clear and concise way of doing it. And no one can really sort of, accuse you of not doing enough work. And to be honest, I can't really fully see the pivots. I mean, you can kind of like, what's going to happen, but show that it's going to happen, right? Don't just, stop and be lazy about it. We want to show all of our work. So it's right at this step that I can see the pivots perfectly, right? Here's my pivot, here's my pivot, here's my last pivot. I'm one step away from a full-on, fully row-reduced echelon form. Just do it, right? What difference does it make? Go for it, Definitely go for it. But now I know this matrix C is row equivalent to the 3 by 3 identity matrix, which means, since statement B is true, all of these statements on this list are true, and that the matrix is invertible. So we'd say then C is invertible. This matrix D, we're going to skip over this one because I want you to try this one on your own, and then let me know in the comment section below. Let me know what you get from this. But I'm going to give you a hint. I think this is another one that would be good to do the row reduction. And you can do that to either see if you're going to get the identity or not, or you can take a look at the pivot positions. And I think these are statements, we'll go back and we'll check, but I believe these are statements B and C on the list. And I would say those are the best that you're going to get with like a 3 by 3. Yeah, see if it's row equivalent to the identity matrix like we just did, or you could try to see, finding out maybe a bit sooner than that if you have 3 pivot positions, if you're going to have all of the pivots available. So try to see what you get from the row reduction pivot positions, and then I'm going to say, let me know. I want you to try, do a little sample on this one. Try it out. Let me know. Pause the video now, take a look at it, and let me know in the comments what you get. Is it invertible? Is it not invertible? I need to know. Let's take a look at this one here. E, matrix E. Just look at it for a bit. When somebody gives you a matrix and wants to know if it's invertible, just, you know, make fierce eye contact with that person, definitely. Kind of like give it a little scowl too, like kind of like a mean mug, you know? But then I want you to look at the matrix and just kind of stare at it for a bit. Think about it. Take it all in. Take a deep breath. Get that first cup of the day. If you're not drinking a cup of coffee, go get a cup of coffee. Get the person that's asking you to buy you a cup of coffee. Stare at the matrix a bit. You're going to notice something about this one right away. I'm thinking about pivots. We talked a lot about reducing to the identity matrix. I'm thinking about pivots here. I'm also thinking about that as well. Those two statements kind of go hand in hand. It's not really one or the other. One sort of leads us to the other. So if I'm thinking about the identity matrix, if I'm thinking about the pivots, I'm going to notice right away I've got a big problem. There's no way that I can get 3 pivots, because at best I can get a pivot here in row 1, I can get a pivot here in row 2. I would have to row reduce to see that. But in row 3, I'm not going to get a pivot position. It's not going to happen. I have a row of all zeros. There's no pivot in row 3. I'm going to point that out. We'll say no pivot in row 3. Furthermore, if I'm thinking about this being row equivalent to the identity matrix, I'm not going to, like, none of those rows for a 3x3 matrix are allowed to be 0, 0, 0. Right? I'm going to need some pivot in there. This is not, so I can also say, well, because of this row of all zeros, it's a very bad thing to have here. This is not row equivalent, meaning I can't row reduce it to the identity. So right away, just by looking at this one, we can start making some arguments. Not going to have enough pivots, or not, so we would say, so we get the idea here. We need 3 pivots, not possible, which means the matrix is not invertible. So E, matrix E, is not invertible. We got one more to look at here. We have matrix F. I think we got, yeah, I got more for you, of course. We'll take a look at F here. Let me switch colors so, you know, it doesn't all kind of bleed together. If I look at matrix F, there's a couple of arguments I can make here as well. So I have this column of all zeros, which kind of spells the same trouble as what I talked about before, but I could think about this in a bit of a different way. I think there's actually 2 very clever arguments to make about this matrix F. And the first one is talking about the columns. So we could say the columns of matrix F form a linearly dependent set. Because remember we said if I have a set of vectors, I have first column vector, second column vector, third column vector. If I have a set of vectors and one of those vectors is the 0 vector, then the set is automatically linearly dependent, automatically. Right? So I'm automatically forced into a dependency relationship. Since the columns form a linearly dependent set, I know that statement E is false. Right? So it says the columns must be a linearly independent set. No. I have the 0 vector for one of my column vectors. The columns cannot be independent, so then the columns form a linearly dependent set, which means that all of these items are false, which means that the matrix is not invertible. So here we go ahead and say this means that F is not invertible. Another consideration that I think is really interesting to consider here, though it might be sort of a bit more time consuming, is to talk about this last item on the list. We're saying if a matrix is invertible, then the transpose of that matrix must also be invertible, and vice versa, right? So if I want to consider the transpose of this matrix, which here we're calling it F instead of A, but if I consider the transpose of this matrix, which means I'm going to exchange the rows for columns. So this first row, 3, negative 10, 0, becomes the first column in order, 3, negative 10, 0. The second row, 7, 15, 0, becomes the second column, 7, 15, 0. And the third row becomes the third column, 6, negative 7, 0, but now as a column, 6, negative 7, 0. And now I have this row of all zeros because I've transposed this. And now I can make all of the same arguments that I made for this matrix that just was before it, right? We'd say, well, okay, so we already talked about something that had this row of all zeros. I can't get enough pivots. I'm not going to be able to row reduce the identity. Similarly, I would need 3 pivot positions. I'm not going to be able to do it, so this matrix is not invertible. So we could also make the comment here. Let me actually get a different color. I'll switch back to yellow because I'm so boring. We'll say F transpose is not invertible, which then means, because that's the last item on our current version of our list, this implies right away that F is not invertible then. Just another consideration. Do you have to show it 2 different ways? No. I think it's kind of cool if you do that. If you really push the idea home. Let me know what you know. But it's just another possibility, another consideration. So not invertible. And remember what we said about a matrix that is not invertible. We could also refer to that as a singular matrix. Just a keyword. Do you have to use it? No. A singular matrix is a non-invertible matrix. Just trying to teach. Let's take a look at one more example here. We have matrix G. Now we got a 4x4. So now we're thinking, okay, what can I do here? I think the best option for us is going to be the row reduction. See if it row reduces to the 4x4 identity. Talk about pivot positions. As soon as you get away from a 2x2 matrix, it starts to become, that's sort of the idea. Is it the only way to do it? No. It depends on what the matrix is, of course. If you have a column or a row of zeros, you have a faster argument. But otherwise, I think it's going to be the most use you're going to get out of the invertible matrix theorem. So let's go ahead and let's start row reducing. Now, what do I want to do here? I want to maybe swap around some rows. I'm going to put rows 1 and 2. I'm going to switch them. Put row 2 on top, row 1 next. So that means my top row is 1, 0, 3, 1. You know I want to do that because I have this leading 1. And then row 2 is going to be my former row 1. That's 2, 3, 1, 5. And then I'm just going to go ahead and leave those other rows alone. Just rewrite them. Just rewrite them. Now I'm going to use this 1 in the upper left corner to get zeros underneath it. Already there for rows 3 and 4, but here row 2 needs some row reduction. So I'm going to replace row 2 with row 2 minus 2 times row 1, right? I need 2 minus 2 times 1 to give me that 0. So that's row 2 minus 2 times row 1. So I'm going to rewrite row 1. In row 2's position, I get 2 minus 2 times 1 is 0. 3 minus 2 times 0 is 3. 1 minus 2 times 3, that's 1 minus 6 gives me negative 5. And 5 minus 2 times 1, 5 minus 2 gives me 3. Now, I'm going to go ahead and do some more work here. What I could do next, for example, is I could row reduce in, let's go ahead and do the row reduction in row 4. I'm going to replace row 4 with row 4 minus row 3. I'm just taking advantage of the fact that they have the same entries right at the start so I can get some more zeros happening here. Does this follow an algorithmic row reduction etiquette? No. But we're humans, and if I see that move, I'm going to want to make it. So 0 minus 0 gives us 0. 2 minus 2 gives me a 0 that I wanted to get. 3 minus negative 3, that's 3 plus 3 gives me 6. And 1 minus 2 gives me negative 1. So I'm just making some extra moves here. These aren't going to be bad decisions. I'm just getting some more work out of the way. Now if I'm looking at row 2, I'm just kind of one more 0 away from it being almost reduced. I'd need to scale as well if I'm thinking about the row reduction steps. But what I can do, and I don't like to work with fractions because arithmetic makes me nervous, I'm going to scale these both up. I'm going to do 2 times row 2 and 3 times row 3. So I can get a 3 times the 2 and a 2 times the 3, right? I'm going to do 2 times row 2, 3 times row 3. So if I do 2 times row 2, it's going to give me 0, 6, negative 10, 6. And 3 times row 3, I'm going to get 0, 6, negative 9, 6. You can see what I'm trying to do. I'm trying to make these look similar so I can do some subtraction. I'm just going to rewrite row 4. Now I can do the row reduction that I wanted to do. So I'm going to go to row 3 and replace row 3 with row 3 minus row 2. So I'm going to rewrite rows 1 and 2. Then in row 3's position, I'm going to get 0 minus 0 is 0, 6 minus 6 is 0, negative 9 minus negative 10, that's negative 9 plus 10, gives me 1. And 6 minus 6 gives me a bonus 0. And I can rewrite row 4. So looking really good so far, right? Looking really good. Now what I can do is I can go ahead and scale back here in row 2, but I'm actually going to maybe save that for later because I want you to notice, so I'm not going to necessarily go in order. The next step I would want to do is maybe to scale row 2, and that's fine. It'll give me fractions, not the end of the world. I'll leave them as integers for now. I could reduce it back to its, smaller numbers. That's fine. I'm not going to worry about it. What I'm noticing right away is what's happening in row 3. I have all these zeros, and then my perfect pivot 1. I can get zeros above and beneath it very safely, very surgically, and I want to do that. So how is it going to look? Well, I'm going to replace row 1 with row 1 minus 3, row 3. I'm going to replace row 2 with row 2 plus 10, row 3. And I'm going to replace row 4 with row 4 minus 6, row 3. Those are going to give me those zeros where I want them. So let me rewrite row 3, since it's going to be doing all the work. But then in row 1, I'm going to get 1 minus 3 times 0 is 1, 0 minus 3 times 0 is 0, 3 minus 3 times 1 gives me that 0 that I wanted, and 1 minus 3 times 0 gives me 1. In row 2, I'm going to get 0 plus 10 times 0 gives me 0, 6 plus 10 times 0 gives me 6, negative 10 plus 10 times 1 gives me the 0 that I wanted, and 6 plus 10 times 0 gives me 6. And then in row 4, I'm going to get 0 minus 6 times 0 gives me 0, and then again, 6 minus 6 times 1 gives me the 0 that I wanted, and negative 1 minus 6 times 0 gives me negative 1. And this looks great. Right, we're almost done with this. You could make a comment about pivots, but I don't want to leave this. I want to row reduce all the way. So I'm going to go to row 2, and I'm going to scale it now. I get a really nice scaling, 1/6 row 2. It's a 0 there. And I'm going to scale row 4. I'm going to do negative row 4. Just flip the sign, 0, 0, 0, positive 1. And you can see where we're going with this. Now all I have to do is some work in rows 1 and 2. I want row 1 minus row 4, row 2 minus row 4. I can rewrite rows 3 and 4. In row 1's position, I'm going to get 1 minus 0 gives me 1, 0 minus 0, and then again gives me zeros. 1 minus 1 gives me that 0 that I needed. In row 2 minus row 4, 0 minus 0 gives me 0, 1 minus 0 gives me 1, 0 minus 0 gives me 0, 1 minus 1 gives me that 0. Fully reduced. I have the 4x4 identity. So we'll say this reduces to the identity, which means that matrix G is invertible. So matrix G is invertible. More practice row reducing doesn't hurt either. We have our answer. Looks great. We'll take a look at one more question for this section. we're going to go back to talking a bit about linear transformations and tying it into invertible matrices. So a definition and a theorem. A linear transformation T, mapping from Rn to Rn, is said to be invertible if there exists a function S that maps from Rn to Rn, such that S of T of x gives us x for all x in Rn, or that T of S of x gives us x for all x in Rn. And we're used to this as like an inverse function back maybe in pre-calculus. We'd say, well, if I apply an inverse function to its function, however I build that composite function, doesn't matter which is the inner, which is the outer, it is going to give us the input back out, right? And we've seen this with, for example, e to the x and ln of x, right? We remember e to the ln of x gives us x, and there's a bit of a restriction here that x has to be greater than 0, but otherwise works as an inverse. But then if I do the inverse relation in the other way, natural log of e to the x, here e to the x is always going to be positive and non-zero. This is also going to give me x. So it doesn't matter how I build composite functions. If I have true inverses, it's going to spit back out the input, so to speak. They're going to undo one another, is really the idea. And we're saying that we can hopefully achieve this with linear transformations with what we're doing in linear algebra. I have this theorem to follow up with this, saying we'll let the transformation T, mapping from Rn to Rn, be a linear transformation, and let A be the standard matrix for T. Then T is invertible if and only if A, that standard matrix of the transformation, is an invertible matrix. In that case, the linear transformation S that we were talking about earlier, you can think of it as a function, S of x is equal to A inverse times x. And that's the unique function satisfying these properties that we just talked about, that we can apply them as inverses. And let's see if we can do this for this example. It's not going to be so bad. I think it's going to be maybe a little bit easier than we're even sort of thinking now. So here I want T to be my linear transformation from R2 to R2. I want to show that T is invertible and find a formula for T inverse. Now the first thing that I'm going to do, and this gives me an interesting functional notation, and it's okay to have this functional notation. Otherwise, what I could do is I could try to write it as a matrix, and you could go right to the matrix from this. I don't think it's necessary to do this, but if I want to, I could think of this in terms of like a vector notation. We would say, well, if I apply my transformation T on, let's say, a vector with a first entry x1 and a second entry x2, then it's going to spit out, here I'm going to get another vector, and the first entry of that vector is the first entry in the functional notation, which is 2x1 minus 8x2. And the second entry of that vector is negative 2x1 plus 7x2. And if I want to write this as matrix multiplication, I could build a coefficient matrix times the vector x1, x2. And the coefficient matrix is just going to take these coefficients, 2, negative 8 for the top row, 2, negative 8 for the top row. Second row is going to be negative 2, 7, negative 2, 7. And if I go through and do the multiplication, it's just going to build back, right? 2 times x1 plus negative 8 times x2 is this top entry. We do the row vector rule, negative 2 times x1 plus 7 times x2. But now I can see that this is what we're really describing. We're talking about matrix multiplication, right? I want to find this A inverse times x for S of x, but here I have T of x equals A times x. So transformation on x is A times x, and this is my matrix A. Now, if we're looking at this matrix A, chances are if I'm given this functional notation, I can probably find that matrix just right away. Do I have to write it this way? Maybe not. I can see what's going on here. I can say, well, that's going to be my top row, that's going to be my bottom row, and I just want a coefficient matrix. So I can build that matrix A that way. But here we've showed lots of supporting work, which is always really nice. My matrix A. So what I want to do is I want to find the inverse. Okay, so if I find the inverse of this matrix, then I can build an inverse to my linear transformation. So let's find the inverse here. So we'll say, well, A inverse, if I remember that formula from earlier in the course, I would want 1 over, then I would multiply along the main diagonal, that's 2 times 7. And then I want to subtract away from this, I want to multiply on the off diagonal, that's negative 8 times negative 2. And this is a coefficient that's going to scale into the following rearrangement of the matrix. On the main diagonal, the 2 in the upper left, the 7 in the bottom right, we're going to swap those. So in the upper left is going to be the 7, Bottom right is going to be the 2. On the off diagonal, I'm going to keep those entries where they are, but I'm going to flip their signs. So the -8 is now going to be +8, but it's going to stay where it is. The -2 is going to stay where it is, but I'm going to flip its sign, so it's now +2. And now I just have to go through the rest of the work here to build this inverse matrix. So here we can go ahead and do this. I would say, well, this is going to be, if I find this coefficient, let me do a little bit of scratch work here. That's 1/14 minus, and then here, negative times negative is positive, 8 times 2 is 16, times this matrix. So then this coefficient, that's really 1/-2, so that's a -1/2, times this. So we'll say, well, let's go ahead and build this inverse matrix. If I flip the sign and divide by 2, I'm going to get -7/2. Here I'm going to get -4, and then -1, -1. And this is my inverse, A inverse. So now if I want to build that inverse to my linear transformation, that function s of x, I'm staring at it right now. And I'm not going to be too much of a stickler for the notation on this, so I'm just going to reuse x1 and x2 again. But, you know, you could probably be a little bit fancier with the notation and give everything like a hat notation or something else. But we'll say here for the inverse, s of x1, x2 is going to be given by, and here I can do a functional notation as well. This is going to be a first entry, -7/2 x1 minus 4x2, coming from that top row, and then a comma separating. My second row is going to be the second output. That's -1 x1, or just negative x1, and then plus -1 x2, so minus x2. I'm just building it from here, right? So -7/2 x1 minus 4x2, that's the first thing. -1 x1, -1 x2 for the second thing. And this is my inverse. You can think of it like an inverse function. It's the inverse to this mapping that I have here, t of x. Let me write down what t of x was on this other page, and I want to show you that we can check our work a little bit. So t of x1, x2, that was 2x1 minus 8x2. I'll use this in a different color. So it's 2x1 minus 8x2 and -2x1 plus 7x2. Now, if I want to show that these act as inverses, there's actually 2 ways that I could do this. Let me just show one of the ways. The trick is, or what I want to do, is I want to go to, for example, s of x1 and x2, and I want to treat this entire first output as an input x1, and this entire second, and I'll color code this so it looks really fancy. This second output, I want to treat that as input x2, which is where the notation kind of gets a little bit funny to look at, but it's going to show what we want to show it to anyways. So what I want to do is I want to plug this into the other transformation. I want to plug these in for x1 and x2 into t. So I'm plugging in from s into t, and let's see what that looks like. So then, what is this going to give me? So t of, and let me do my color coding here, because I'm going to be replacing with these special pieces. So I'm going to use the pink x1 that I've underlined, and then the purple x2. I want to show what this is going to look like. So say, okay, so this is going to be a bit of plugging in, but I want 2 times x1, I'll leave some space for that, minus 8 times x2. And then I'll sort of do this, I'm going to need more space, of course, so let me get a little more space, and then -2 x1 plus 7 x2. Scooch down a bit. So I apologize for having to break this up a little bit, but you're going to see the magic anyways. We are here for the magic. Do you believe in magic? So 2 times x1, I'm replacing x1 with this -7/2 x1 minus 4x2. And then minus 8 times x2, but I'm replacing x2 with, in purple, this negative x1 minus x2. And I want to do the same here as well. So this second part here, this negative 2x1 plus 7x2, since I'm already on the purple, I'll replace the x2. x2 I'm replacing with negative x1 minus x2. I'll switch to the pink because I skipped over that. The negative 2 times x1 here, I'm replacing the x sub 1 with negative 7 halves x1 minus 4x2. Looks kind of messy, but all that's really left is to do some simplifying. I'll do the simplifying in a different color so it doesn't all bleed together, but I'll do this in yellow. So now if I multiply this out, well, here we'll distribute, right? So 2 times negative 7 halves x1. The 2's are going to cancel, so I get negative 7 x1. And 2 times negative 4 is negative 8 x sub 2. And here I want to distribute as well, bring the minus sign in along with the 8. So negative 8 times negative x1 gives me plus 8x1. Negative 8 times negative x2 gives me plus 8x2. I want you to notice that the x2 terms are going to cancel right away. Bam, bam. And negative 7x1 plus 8x1 is just going to give us 1x1, or it just spits out x1, which hopefully we were expecting that to happen. It's doing what it's supposed to be doing as an inverse. It's going to spit out x1 first, then the second component is going to spit out x2, hopefully. Let's see. I'm nervous. Let's distribute. Here, the minus signs are going to resolve, and the 2's are going to cancel, so I get positive 7x sub 1. And then negative times negative is positive, but 2 times 4 gives me positive 8x sub 2. And here I'm distributing some more, so we're going to get negative 7x1 and then negative 7x2. And if I'm simplifying, I want you to notice now that x1 terms are going to cancel. 7x1 minus 7x1 is gone, bam, bam. And the other ones are going to combine, right? 8x2 minus 7x2, that's going to give me 1x2. So this actually spits out, in order, x1 and then x2, just like we said it would. So what did we do is we took transformation t, we plugged s into it. T of s of x1, x2, spat out x1 first and then x2 back out. Or in just an even shorter shorthand notation, t of s of x just spits out x perfectly back out. And this is one way you could show it. You could also show that it holds true in the other direction, that s of t of x gives you x back out, which is just doing very similar work, but the opposite order. But yeah, you could show it that way too. Really cool stuff. Hey, I hope you enjoyed this. We're going to be back talking about more linear algebra. Our journey's not over, right? So don't even think that we're ending it here. We're just, moving on. We're going to talk about some slightly different topics. We're going to connect it back to old things, and we're going to see the invertible matrix theorem a lot more. Let's go take a second peek at it, just because I think it's a lot of stuff. It's really cool. There it is. Invertible matrix theorem. Gotta love it, gotta have it. Hey, yeah, no matter where you are and what you're doing, I want to make sure that you're going to keep learning, keep dreaming, and always follow your heart. You know where to find me if you need me. Until then, take care, and I will see you next time.